Welcome to the Depth Dive. Today, we're cracking open a really complex and honestly fast-moving field, artificial intelligence in medicine. AIM, as they call it.
Yeah, and it's more than just a tech upgrade, isn't it? It feels like a fundamental shift.
Absolutely. It's changing everything. I mean,
Yeah.
from diagnosing skin conditions to designing brand new drugs. It's huge.
It really is.
So, our mission today, what we want to do is give you a real shortcut to understanding this whole landscape. We'll trace the history, starting way back with those early attempts in the 60s, look at the data revolution, and then land on today's most impactful systems, especially those clinical decision support tools.
Right. We're looking for those key moments, that sort of aha insight.
Exactly. Why did it take off now? And how does it actually change things for patients?
And understanding that framework is so important because, look, the story of AI in medicine isn't just one invention.
Yeah.
It's really about the infrastructure, the plumbing, finally catching up with the ideas. So we need to grasp the cool stuff happening now, sure, but also those historical hurdles, the lack of data, the weak computers.
All the things that held it back for decades.
Precisely. All the things that needed tearing down before this could really scale beyond just a lab experiment.
Okay, so let's unpack that evolution. We always hear AI started conceptually in the 50s, but what did it actually look like when people first tried applying it to something as, well, messy as human health?
Yeah, it was very rule-based, almost painfully so, looking back. The first real tries were in the 60s and 70s. They were building what they called expert systems.
Right. MyCIN is the famous one.
MSCIN, exactly.
Yeah.
It was designed to help doctors diagnose certain bacterial blood infections and recommend treatments. But here's the key thing, the thing you have to understand.
Yeah.
It didn't learn from data, not like AI does now.
So it's basically just a massive flowchart, like if this, then that.
That's a great way to put it. Thousands of if-then rules all programmed in by human experts. If the patient has symptom A and lab result B is positive, then it's probably diagnosis X. It was trying to mimic human reasoning.
Not detect patterns on its own.
Not at all. And that reliance on human-coded rules, well, that was its biggest weakness. Its Achilles heel, really.
Because if the human expert missed something or there was a really rare case...
The system just broke.
Yeah.
Couldn't handle it.
Yeah.
And the source material we looked at really lays out those limitations clearly. You had terrible computing power by today's standards.
Right.
The algorithms were these basic rule trees. But the biggest issue, not enough good, standardized digital data to train anything smarter.
You can't teach something to recognize patterns if there are hardly any patterns to show it.
Exactly. It's like trying to teach a kid to read with only one page from a book.
So the next couple of decades, the 70s through the 90s, that was like the quiet preparation time.
That's a perfect way to describe it. AI itself felt a bit dormant, but the foundation was being laid.
And that foundation was digitizing medical records, the big shift to EHRs.
Yes. Electronic health records. That's the piece of the puzzle people often forget. It was a painful transition for doctors at the time, we know that. But without those huge, structured, searchable data sets, that digital paper trail,
We wouldn't have modern AI in medicine.
you just wouldn't. The industry was, maybe without fully realizing it, creating the food source for machine learning. It finally had something to chew on.
Okay, so now the tech starts to catch up. Early 2000s, and the big buzzword becomes deep learning. What was it about deep learning that finally broke through those old limitations?
What was so interesting is that deep learning flipped the whole approach on its head.
How so?
Remember those old systems needed humans to tell them what features to look for? Look for a fever, look for this cell shape.
Right.
Deep learning, using these things called neural networks, could just take in the raw data, like a raw X-ray image or messy doctor's notes, and it could teach itself which patterns, which features were actually important for the task. It could handle complexity that those old rule-based systems couldn't even begin to process.
So instead of being spoon-fed the rules, it learned the rules from the data itself.
That's the core aha moment right there. And that's what made AI suddenly capable of interpreting really messy, complex stuff like medical images or genetic data at a huge scale.
And that unlocked, well, pretty much everything we see now.
Pretty much. It was the key.
So looking at the last, say, 10 years, the progress feels incredibly real, very tangible, across the whole medical field, really.
Absolutely.
We've seen massive improvements in detection and diagnosis, AI algorithms spotting things the human eye might just skim over.
For sure, that image analysis capability is profound. Think about finding cancer earlier because AI helps read the scans better,
Yeah.
or spotting tiny signs of diseases progressing. And this links directly into personalized medicine, too. Well, AI can look at your specific genetic code, your lifestyle data from wearables, your medical history, all of it, and suggest a treatment path that's statistically optimized just for you.
Moving away from that one-size-fits-all model.
Exactly. Tailoring medicine down to the individual level.
And it even extends right into the operating theater. We hear about robotic surgery, but it's not just the robot holding the scalpel, is it? What's the AI doing?
It's about enhancing control and precision. The AI helps by, say, filtering out tiny natural hand tremors from the surgeon.
Oh, interesting.
It provides better visualization, maybe highlighting nerves or blood vessels. And some systems now use real-time data during the surgery to help the surgeon plan the best path for an instrument or identify things hidden by blood.
So it turns a manual process into something. Data enhanced, hyper precise.
You got it. Data-augmented surgery.
Incredible. And outside the hospital, maybe more behind the scenes, where's AI having the biggest impact commercially?
I'd argue it's in the pharmaceutical world. Accelerated drug development?
Right. Finding new medicines faster.
Massively faster. Instead of spending years and millions in a wet lab, testing chemical compounds one by one, machine learning models can predict if a potential drug candidate is likely to work, if it might be toxic, how it might interact with the body, all before you even start physical testing.
Wow. So it cuts down that discovery time dramatically.
From years potentially down to months, it's a huge efficiency gain.
It acts like a super powerful filter for potential new drugs. Okay, so that's the high-tech lab stuff. But what about the everyday experience? When you, the listener, walk into a hospital, how is AI changing things there?
It's often working invisibly in the background. In medical imaging, for instance, AI might be doing a first pass on your scan, flagging areas for the radiologist to look at more closely.
Prioritizing their workload.
Exactly. And in hospital operations, AI helps manage resources better, predicting when patients might be discharged so beds can be ready, optimizing nurse schedules, things that make the whole place run smoother.
Reducing wait times, hopefully.
That's the goal, improving efficiency and the patient experience.
Oh. And then there's the stuff that interfaces directly with us, the patients. AI as a sort of health co-pilot.
Yeah, definitely. Think about apps exploring AI for spotting early signs of mental health issues, just based on subtle behavioral changes. It's early days, but promising.
Okay.
Or those AI apps giving you personalized diet advice based on your blood sugar monitor readings.
Right, I've seen those.
And of course, the AI built into wearables, constantly tracking your heart rate, your sleep, your activity, offering continuous health monitoring tailored to you.
So that brings us nicely to our main focus. The system's designed to pull all this complexity together for the doctor or nurse. Clinical decision support systems, CDSS. At its heart, this is AI designed to help the human expert, right? Analyze data, spot patterns, give useful advice.
Exactly. Its AI is an augmentation tool. It takes in these enormous data sets, learns the patterns, and ideally delivers clear, actionable recommendations right at the point of care.
And this is where all those technologies we mentioned really come together.
Precisely. The core applications within CDSS lean heavily on deep learning. Take diagnosis and prediction. We talked about deep learning finding features in data.
Yeah.
Well, the workhorse model for that, especially in medical images, is the convolutional neural network, or CNN.
Okay, CNNs. We hear that term a lot. Can you break that down simply? What does it do?
Okay, think of a CNN like a series of specialized filters for images. It doesn't just see a picture like we do.
Right.
It processes the image through layers. The first layer might just detect simple lines and edges. The next layer combines those lines and edges to spot textures. Later layers combine those textures to find more complex shapes, maybe the specific boundary of a tumor, or the subtle signs of fluid in the lungs on an X-ray that might be invisible to the naked eye.
So it builds up understanding layer by layer, from simple features to complex objects.
Exactly right. It recognizes patterns within patterns, right down at the pixel level.
Which is why they're so good for X-rays, MRIs, pathology slides.
That's it. They're being used right now to help diagnose skin cancer from photos, spot diabetic eye disease from retinal scans, often faster and sometimes more accurately than humans. They can even predict heart failure risk from imaging biomarkers. These are real, concrete benefits.
Okay, so CNNs handle the pictures. What about all the written stuff? The doctor's notes, patient histories, discharge summaries, all that text.
That's where natural language processing, or NLP, comes in.
Right.
Clinical notes are messy, right? Doctors use shorthand, abbreviations, they dictate things. It's not structured data.
Definitely not.
NLP's job is to read all that unstructured text, figure out the medical meaning, and pull out structured information, like identifying a specific drug name and dosage, or noting a family history of heart disease mentioned in passing.
So it translates the doctor's narrative into data the computer can actually use.
Precisely, which is crucial for populating those electronic health records accurately. And that structured data then feeds back into the other AI models, like for prediction.
I see. So it connects the text to the analytics.
And that directly enables better personalized treatment within the CDSS. The system can analyze your history, structured by NLP, your images, analyzed by CNNs, maybe your genetic data.
And then suggest the best treatment plan for you.
Yeah, maybe recommend an optimal drug dose, flag a potential risky drug interaction, or suggest a different therapy based on how it predicts your body might respond, tailored specifically to you.
And the final piece seems to be just making things run smoother, workflow efficiency.
Absolutely. By helping automate some documentation tasks or providing quick summaries and recommendations, CDSS aims to free up clinicians.
Less time clicking boxes, more time with the patient.
That's the ideal, yes.
Yeah.
Leveraging AI not to replace the clinician, but to be like a superpowered assistant. A tireless second opinion that filters noise and highlights what's critical.
Okay, so we've gone from IMYCIM's simple rules through the absolute necessity of digital data to today's incredibly sophisticated CDSS using CNNs and NLP. It's clear AI's power is in handling complexity and scale that humans just can't match.
Undeniably.
But it's not everywhere yet. What are the big hurdles? What's stopping this from being in every clinic tomorrow?
Well, there are some pretty significant roadblocks. First up is interpretability and transparency. The black box problem.
Meaning doctors don't know why the AI suggested something.
Exactly. And clinicians, quite rightly, are hesitant to trust a recommendation if they can't understand the reasoning behind it. How can you justify a treatment decision to a patient or even a colleague if the AI's thinking is completely opaque?
Yeah, that's a major trust issue. You need to be able to explain it.
We need systems that can provide some kind of explanation for their outputs. That's a big area of research.
Makes sense. What else?
Then there's the massive challenge of bias and fairness. This really comes down to the data used to train these algorithms.
How so?
Well, if an AI is trained mostly on data from, say, one specific population group or geographic area.
It learns the patterns for that group.
Right. And it might perform badly or even give harmful recommendations for people from different backgrounds who weren't well represented in the training data.
So ensuring the data is diverse and representative is crucial for fairness.
Absolutely critical. If we don't get that right, AI could actually worsen health inequalities. We need equitable data to get equitable outcomes.
And all this relies on handling incredibly sensitive patient information. So data privacy and security must be huge.
Paramount, non-negotiable. We're talking about needing really robust security, like military-grade stuff, plus strong rules and governance for how this data is handled, stored, and used. Protecting patient confidentiality is fundamental.
Okay, interpretability, bias, security. What about just getting doctors and nurses to actually use it?
Yeah. The integration challenge. Fitting these sophisticated AI tools into existing hospital workflows, which are often based on older systems and established habits, is really hard.
I can imagine. Resistance to change is natural.
It is. The interfaces need to be super intuitive, genuinely helpful, and not just add more clicks or administrative burden. You have to overcome clinician skepticism by proving the value, making it seamless. It needs to feel like an assistant, not an interruption.
What a journey we've covered. From IMYCIN realizing data was key, to today's CNNs predicting disease from scans and robots helping in surgery. AEM's strength is definitely processing that complexity, that speed, and giving insights back to the human expert.
And that core goal, improving the quality of care, making it more efficient, that's still the driving force. Future success, I think, hinges less on inventing brand new algorithms now, and more on getting the implementation right, making sure these systems are transparent, fair, secure, and truly helpful in practice.
And the source material really emphasized that this needs true teamwork, doesn't it? Clinicians, data scientists, engineers, policymakers, all working together.
Absolutely. It has to be interdisciplinary.
So here's a final thought for you, the listener. If AI's real power comes from synthesizing all this diverse information, how quickly can medicine itself overcome its own traditional silos? How fast can clinicians, researchers, IT departments, administrators truly integrate their efforts to unlock the full potential of this technology? That speed of convergence, that breaking down of internal barriers, maybe that's the biggest question mark for the future of healthcare.